Welcome to Space Sleep. Tonight, we will drift slowly through the deepest regions of space, not the familiar warmth of the inner solar system, but the silent, unlit, and terrifying vastness that lies far beyond, where even light becomes weak, and where reality itself begins to feel distant. As you settle in, while you're getting comfortable, take a brief moment to like and subscribe, only if you are truly enjoying this. And tell us in the comments the location and time where you are watching right now, so we can drift into the deep space together. Now, get comfortable and prepare to travel into the coldness of deep space. Imagine a place where there is no up, no down, no direction at all. A place where silence is not peaceful, but absolute. Not the silence of a quiet room, but a silence so complete that sound itself cannot exist, because sound needs air, and there is none. Imagine distances so extreme that entire civilizations of time would pass before anything could cross them. Imagine emptiness so total that a single atom might drift alone for millions of years without touching anything else. And somewhere within this unimaginable vastness, there is everything we think we know. Stars, planets, life, and us, all floating inside an ocean of almost perfect nothing. Our journey begins not with light, but with its absence. Deep space, the regions between stars, the void where even starlight grows thin, stretched, and swallowed by distance. And the first horror we encounter here is not something that moves. It is something that never changes. Cold. A cold so absolute that it is not simply freezing. It is the absence of all heat, all vibration, all energy that we associate with existence. If you were to drift into deep space without protection, your body would not feel cold in the way we understand it on Earth. There would be no wind, no touch of ice, no dramatic moment of freezing. Instead, heat would silently leave your body, radiating away into nothing, molecule by molecule, until every internal process slows and stops. Space does not freeze you like a winter night. It empties you. The background temperature of deep space between stars is only a few degrees above absolute zero, roughly 2.7 Kelvin, a temperature so low that atoms themselves begin to lose motion, approaching a state where physical activity becomes almost meaningless. Even light, when it finally reaches such regions, feels ancient, weakened, stretched into microwaves that carry the memory of the early universe. This is the cosmic microwave background, a faint afterglow of creation itself, not warmth, but a whisper of what once was. And in this endless cold, there is no shelter, no corner of slightly warmer space waiting to save you, because space is not filled with cold air. It is filled with nothing, and nothing cannot hold heat. Now imagine something even more disturbing. You are not falling into ice. You are not sinking into snow. You are drifting into a vacuum where every direction leads to the same outcome. Energy loss, isolation, stillness. Far from any star, molecules drift apart so widely that collisions become almost impossible. Matter becomes sparse, almost imaginary. A hydrogen atom might travel for centuries before encountering another, and even then, there is no warmth exchanged in any meaningful way, only endless separation. In these regions, the universe becomes a machine, slowly cooling down, a clock that is running out of energy, but so slowly that no human lifetime could ever witness its end. And yet, within this unbearable cold, something strange happens. Coal does not just preserve, it transforms. Gas clouds, drifting in deep interstellar space begin to condense, not because they are warm, but because gravity is patient. Over millions of years, particles gather, slowly, reluctantly, as if even matter resists the idea of coming together in such emptiness. These clouds become stellar nurseries, regions of darkness that slowly ignite into stars. But even this process is violent only in theory. From a distance, it is almost imperceptible, a faint thickening of nothing, and then light is born again. But light does not erase the cold, it only pushes it back temporarily, because beyond every star's reach, the cold is waiting, always waiting. Now imagine drifting further, past any familiar system, past any source of warmth, into a region where not even a single photon from a nearby star has reached in millions of years. Here, darkness is not the absence of light. It is something heavier, something almost physical, a darkness so complete that your mind would lose reference points. No horizon, no shadow, no reflection, only the realization that seeing itself depends on something that is no longer present. In such places, even time feels different. Without events, without change, without motion to measure against, time becomes meaningless. A second, or a million years, would feel identical, and then there is the silence. Not silence as we know it, but the absence of any medium that could carry vibration. No air, no sound waves, no echo, not even the possibility of an echo. If something exploded here, it would not roar, it would vanish without announcement. A violent event reduced to pure geometry and energy dispersal without sensation. And still, the cold continues, spreading, equalizing, reaching everywhere. Even light, if left alone long enough, is stretched by expansion itself, shifted into lower and lower energies until it fades beyond detection. This is the slow suffocation of the cosmos, not a dramatic end, but a gradual loss of everything that can carry warmth, motion, or meaning. And as you drift deeper into this region of deep space, something begins to feel wrong in a quiet way. Not danger in the way we understand it, but absence. The absence of stars in every direction should not feel like anything. And yet, it does, because the human mind evolved under skies filled with points of light. And here, there are none. Only distance, only cold, only the feeling that you are moving through something that does not acknowledge your existence at all. And far ahead, beyond this region of almost perfect emptiness, there are colder places still. Regions where even the faint heat of interstellar space is no longer present in any meaningful amount. Places where matter becomes so rare, so spread out, that the universe resembles not a structure, but a memory of structure. And in those deeper regions, something even more unsettling begins to emerge, where temperature approaches limits so extreme that conventional physics begins to behave in ways that feel almost alien, as if the universe is slowly forgetting how to be anything at all, drifting further into states where even the concept of heat becomes irrelevant, and where the last remaining photons travel endlessly through expanding darkness, until they too are stretched thinner, and further still into wavelengths so large they barely interact with reality anymore, continuing outward into regions where even gravity itself becomes the only remaining architecture, holding anything together across unimaginable distances. And beyond that threshold, beyond the last trace of starlight, there is only the next layer of cold, waiting quietly in the dark as we continue deeper into the places where the universe no longer resembles anything familiar, and where the true nature of deep space begins to reveal itself even further, where the last traces of structured energy stretch themselves across an expanding fabric that never stops growing. And as we continue deeper into this silent architecture of nothing, we begin to encounter regions not defined by objects, but by the absence of objects on a scale so large that even galaxies become rare exceptions rather than expected features. These are the cosmic voids, enormous regions of space, spanning tens to hundreds of millions of light years, where the density of matter drops dramatically compared to the cosmic average, not empty in a perfect sense, but close enough that the distinction becomes almost meaningless from a human perspective. In these voids, a single galaxy might be separated from its nearest neighbor by distances so vast that light itself would take millions of years to cross the gap, and between them, only hydrogen atoms, stray photons, and the faint relic radiation of the Big Bang continue to drift outward. Even here, the temperature is not truly measurable in a conventional sense, because temperature in space is not defined by air or wind, but by radiation fields and particle energy distributions. And in these voids, the dominant background remains the cosmic microwave background, that faint afterglow of the early universe, now stretched by cosmic expansion into microwaves, with a temperature of approximately 2.725 Kelvin, a number so precise, so consistent across the sky, that it becomes one of the most important measurements in cosmology. But even this uniformity hides something unsettling, because the universe is expanding, and not only expanding, but accelerating, driven by what we call dark energy. Space itself is stretching between gravitationally bound systems, not galaxies moving through space like explosions, but space itself expanding everywhere at once. Distances grow, photons lose energy, wavelengths stretch, light becomes redshifted, then infrared, then microwave, and eventually longer than anything we can directly detect. This process has a consequence that is almost incomprehensible in scale. Distant galaxies are slowly disappearing from our observable reach, not because they vanish, but because space expands faster than light can bridge the growing gap. From certain vantage points in the far future, entire regions of the universe will become causally disconnected. A cosmological horizon, similar in concept to an event horizon, but driven by expansion rather than gravity. Beyond that horizon, galaxies still exist, stars still shine, but no signal from them will ever reach us again. And as you drift through this expanding darkness, you begin to realize something even more unsettling. The universe is not only cold, it is getting colder, because as space expands, energy spreads thinner. Photons lose energy density. Matter becomes more isolated. Heat becomes harder to transfer. In the distant future, even black holes will dominate the energetic landscape. Black holes, the most extreme gravitational objects known, regions where space-time curvature becomes so intense that not even light can escape. At their boundaries, the event horizon, physics reaches a point of no return. Cross it, and every path leads inward. Even now, in deep space, isolated black holes may drift silently between galaxies, invisible unless they actively consume matter or emit radiation from accretion disks. And yet, even black holes are not eternal. According to quantum field theory in curved spacetime, they are expected to slowly emit Hawking radiation, a faint thermal emission caused by quantum effects near the event horizon, so weak for astrophysical black holes that it is effectively undetectable at present times, but theoretically persistent over unimaginable durations. This means something profound. Even the darkest objects in the universe are slowly evaporating, slowly losing mass, slowly releasing energy, slowly fading into nothing. But the timescales are so extreme that they dwarf almost every other process in cosmic history. A black hole with the mass of a star would take far longer than the current age of the universe to evaporate significantly. Supermassive black holes, found at the centers of galaxies, would persist even longer, surviving far beyond the era of stars themselves. And when the last stars eventually burn out, the universe will enter what physicists sometimes call the degenerate era, a time dominated by white dwarfs, neutron stars, and black holes. But even that is not the final stage, because as expansion continues, even these remnants will become isolated, each object drifting alone in an increasingly empty cosmic arena. No new stars forming, no new heavy elements created, no new gravitational structures emerging, only slow cooling, slow separation, slow fading, and the cold deepens again, not because temperature itself has a direction, but because usable energy gradients disappear. Without gradients, there is no work, no motion that can be harnessed, no thermodynamic structure that supports complexity. This leads to the concept of heat death, not as an explosion or collapse, but as a final equilibrium state where entropy reaches a maximum. A universe where energy still exists, but is evenly distributed. No differences, no flow, no transformation, only uniformity across unimaginable scales. But even before that final state, something even more subtle occurs in deep space. Particles themselves become increasingly isolated. Atoms rarely interact. Radiation becomes sparse, and quantum fluctuations begin to dominate local behavior. In near-empty regions, space is not truly nothing. It is a quantum field in its lowest energy state, constantly fluctuating, creating and annihilating virtual particles that exist only for fractions of a second. Even in the deepest void, the universe refuses to become perfectly still. There is always a faint tremor, a microscopic instability in the fabric of reality itself. And yet, none of this changes the overall direction. Everything still trends toward colder, more dilute, more isolated conditions. Even photons that have traveled since the early universe continue to stretch as space expands, losing energy, approaching wavelengths so large that they begin to exceed the size of gravitationally bound structures themselves. Eventually, even these photons will become so diluted that they effectively cease to influence anything, not destroyed, but irrelevant. And as you drift further still, past galaxy clusters, past superclusters like Laniakea, past the faint remnants of large-scale cosmic filaments, you begin to see the universe not as a collection of structures, but as a fading pattern embedded in expansion itself, a pattern slowly being erased by distance. And in this erasure, cold is no longer just a temperature. It becomes the dominant condition of existence. Because without stars nearby, without radiation density, without energy flow, every region of space approaches the same asymptotic state, near absolute zero, but never quite reaching it, a limit that physics allows, but never fully attains. And so the universe continues, not collapsing, not stopping, but stretching itself thinner with each passing moment, while the remaining islands of matter drift farther apart, their light growing weaker, their influence fading, until even the concept of nearby begins to lose meaning entirely as we continue forward into the next layer of deep space, where new phenomena begin to appear at the edge of emptiness, where even the remaining structure of space-time begins to reveal subtler layers of behavior that are not visible in galaxies, but only in the deepest statistical properties of the universe itself. At these scales, we are no longer observing objects. We are observing cosmology, the universe as a physical system, and one of the first measurable facts in this extreme emptiness is the baryon density. Even in intergalactic space, matter is not zero. It is just incredibly diluted. On average, the observable universe contains roughly 1 hydrogen atom per cubic meter in the intergalactic medium, and in cosmic voids, it can drop even lower. This is not a vacuum in the laboratory sense. It is a vacuum stretched across billions of light years, still containing traces of the early universe's matter distribution. Most of this matter is hydrogen and helium left over from Big Bang nucleosynthesis, primordial elements, unchanged for over 13 billion years, drifting slowly under the influence of gravity, but so sparsely distributed that interactions are extremely rare. And alongside this matter, there are other invisible backgrounds permeating deep space. The cosmic neutrino background, a sea of neutrinos created within the first second after the Big Bang. Billions of neutrinos passing through every square centimeter of space each second, yet interacting so weakly that they pass through entire planets without notice. And even deeper still, the gravitational wave background, faint ripples in space-time produced by ancient mergers of black holes and neutron stars, stretching and compressing space itself, but so weak and so diffuse that they form a near-static hum across the universe. This means that even in the deepest voids, space is not truly silent in a physical sense. It is filled with overlapping fields, radiation fields, quantum fields, gravitational perturbations, but none of them carry energy in a way that can sustain structure locally. Now we move further into a different kind of horror, not emptiness of matter, but emptiness of interaction, because in deep space, distance is not just separation. It is isolation enforced by physics. The expansion of the universe follows what is called the Hubble flow. On large scales, galaxies are not moving through space randomly. Space itself is expanding uniformly, carrying galaxies apart like points on a stretching fabric. The further away a galaxy is, the faster it appears to recede. At extreme distances, this recession exceeds the speed of light, not because objects move faster than light locally, but because space itself expands between them. This creates a cosmic horizon, a boundary beyond which no signal can ever reach us. Not now, not in the future, not in principle. Beyond this horizon, there are regions of the universe that are fundamentally disconnected from us forever. They exist, but they are unreachable. And this horizon is shrinking in moving coordinates over cosmic time due to accelerated expansion driven by dark energy, meaning more and more regions will cross it, becoming permanently inaccessible. So as time progresses, the observable universe becomes smaller in a causal sense, not physically shrinking, but losing contact with the rest of reality. Now consider what remains inside our reachable volume. Galaxy clusters, superclusters, filaments of dark matter, voids between them. Even these structures are not stable forever. Gravity tries to pull matter together. Dark energy tries to pull space apart, and dark energy is winning on the largest scales. This leads to the slow dissolution of large-scale structure. Filaments thin out, clusters become gravitationally bound islands, and eventually even galaxy clusters stop interacting with each other. Each cluster becomes its own isolated universe island, a self-contained gravitational system surrounded by expanding emptiness. Within these islands, galaxies still evolve, Stars still form for a time, but only until the gas supply is exhausted. Star formation depends on cold molecular hydrogen clouds collapsing under gravity, but over time, that gas is consumed or expelled by stellar winds and supernova feedback. Eventually, star formation rate declines toward zero, a point known as stellar formation quenching. After that, only long-lived red dwarfs remain active, stars that burn their fuel slowly for trillions of years, far longer than current cosmic age. But even these stars are temporary in cosmic terms. As hydrogen runs out, fusion ceases. White dwarfs remain, cooling slowly over trillions to quadrillions of years. Neutron stars persist, incredibly dense remnants of collapsed cores, and black holes dominate the gravitational landscape. This is the universe entering its late stages of evolution. But even here, the horror is not violence. It is absence of change, because time itself continues, but with fewer and fewer events capable of marking its passage. A universe filled with objects that no longer interact in meaningful ways becomes indistinguishable from one that is frozen, even though it is still evolving in background physics. And then, something even more extreme begins to matter. Particle stability. Current physics suggests that protons may or may not decay depending on unconfirmed grand unified theories. If proton decay occurs, even ordinary matter is not permanent. Atoms would slowly disintegrate over timescales exceeding 10 to the power of 34 years or more. If it does not occur, matter could remain stable far longer, but still subject to gravitational isolation and black hole domination. Either way, the universe trends towards simplification. Complex structures disappear first, then stars, then planets, then atoms themselves become rare configurations in an expanding field of near-nothingness. Meanwhile, black holes continue their slow evolution. They accrete matter when available, but in the far future, there will be nothing left to consume. At that point, Hawking radiation becomes the dominant process. Black holes radiating energy away as thermal emission, their temperature inversely proportional to mass, meaning smaller black holes evaporate faster over unimaginable timescales. Even the most massive black holes will decay. The universe will enter what is sometimes called the black hole era, followed by the dark era. In the dark era, no stars exist. No black holes remain above quantum scale. Only extremely dilute radiation and subatomic particles drifting through expanding space. The temperature of the universe will approach an equilibrium extremely close to absolute zero, but never exactly reaching it, due to quantum fluctuations and de Sitter horizon effects in an accelerating universe. And even then, space itself is not static. Quantum field theory tells us that even vacuum energy is non-zero. The vacuum is not empty. It is the lowest energy state of fields that permeate all of space-time. This means that even the deepest emptiness still contains structure, but structure that cannot be accessed or used. Virtual particles continuously appear and vanish. Space-time itself experiences tiny fluctuations, and horizons associated with accelerated expansion produce thermal radiation at extremely low temperatures. But none of this restores order. None of this reverses isolation. None of this reconnects what has been separated. Instead, it reinforces the final condition of deep space, a universe where everything exists, but almost nothing can interact, where distance becomes absolute separation, where time continues without meaningful events, where energy exists but cannot flow. And as you drift further into this conceptual deep space, beyond even the last gravitationally bound structures, you begin to encounter regions where space-time curvature is dominated not by matter, but by the geometry of expansion itself, where the metric of the universe stretches so uniformly that every point appears locally identical to every other point, and where even the concept of center, or edge, dissolves completely into pure coordinate expansion, leaving only the question of what remains when even structure is no longer distinguishable from emptiness. As we continue deeper into the next stage of cosmic isolation, where the last remnants of interaction physics begin to fail in describing what the universe becomes next, where the final limitation is no longer what exists in the universe, but what is physically possible for anything inside it to reach. Because at this stage of deep space, we are no longer only discussing cosmic structure, we are now confronting motion itself, travel, and the brutal physics that governs it. Space travel in deep space is not limited by engineering alone. It is limited by relativity, by energy, by distance on scales that turn ordinary intuition into something completely invalid. Even the fastest spacecraft ever built by humanity, Voyager 1, travels at roughly 17 kilometers per second relative to the Sunday. That sounds fast on Earth, but in interstellar terms, it is almost stationary. At that speed, reaching the nearest star system, Alpha Centauri, would take over 70,000 years. This is not a failure of technology. It is a consequence of scale, because space is not just large. It is exponentially large compared to human capability. Now imagine deep space travel beyond our solar system. No planets to refuel from, no stars nearby to use for gravity assists. Only the interstellar medium, a near-perfect vacuum with about 1 hydrogen atom per cubic centimeter in denser regions and far less in voids. A spacecraft traveling through this environment faces several fundamental problems. First, propulsion. Chemical rockets are essentially useless beyond planetary environments. Their specific impulse is too low. They require reaction mass that becomes impractical for interstellar distances. Even nuclear thermal or nuclear pulse propulsion, like theoretical Project Orion concepts, only provide incremental improvements. They still operate under Newtonian reaction mass constraints. Second, energy. Any ship leaving the solar system must carry all its energy source with it, or rely on external harvesting. But in deep space, there are no solar panels that can generate meaningful power. The solar flux at interstellar distances drops with the square of distance, becoming effectively zero beyond a few hundred astronomical units. This forces theoretical reliance on advanced systems, fusion propulsion, antimatter engines, laser beaming from home systems, or hypothetical Bussard ramjets collecting interstellar hydrogen. But each of these has extreme limitations. Fusion propulsion requires sustained containment of plasma at millions of degrees. Antimatter requires energy production methods that we currently cannot scale economically or safely. Laser propulsion requires infrastructure spanning astronomical distances. And ramjets face the problem that interstellar hydrogen is too sparse and too ionized for efficient collection. So even in theory, interstellar travel is not simply difficult. It is unstable under most known physical constraints. Now we introduce the third limitation, relativity itself. As a spacecraft approaches significant fractions of light speed, relativistic effects begin to dominate. Time dilation occurs. From the perspective of the travelers, time passes normally, but from the outside universe, time slows dramatically for them. At 99% the speed of light, time dilation becomes extreme. A journey that takes decades externally may feel like only a few years on board. However, this does not solve distance. because acceleration to those speeds requires enormous energy. The relativistic energy equation grows without bound as velocity approaches the speed of light. E equals gamma squared, where gamma gamma increases toward infinity as velocity approaches c. This means that reaching light speed is not just difficult, it is energetically impossible for any object with mass under known physics. So even in the best-case scenario, deep space travel is limited to sublight velocities, and sublight in interstellar terms is slow. Now consider navigation in deep space. Unlike planetary travel, there are no landmarks, no magnetic fields that remain stable over long distances, no atmosphere for reference, no horizon. A spacecraft in interstellar space travels through a nearly featureless coordinate system. Its only references are distant stars, and those stars shift over time due to stellar motion and galactic rotation. This creates navigation drift over long durations. Even tiny errors in trajectory compound over light years. A deviation of microdegrees at launch can result in missing a target star system entirely by millions of kilometers. Now consider communication. Light speed delay becomes absolute. A message sent from Earth to a spacecraft near another star system takes years to arrive. A reply takes years more. Real-time communication becomes impossible. Any interstellar mission becomes a one-way causality delay loop. You do not speak to the mission, you speak to its past. And this is assuming the spacecraft even survives. Because deep space is not empty in a harmless way. It contains high-energy particles called cosmic rays, protons and atomic nuclei accelerated to near light speeds by supernova remnants and black hole jets. These particles carry enough energy to damage electronics and biological tissue. Over time, without shielding, they degrade spacecraft systems through cumulative radiation exposure. Even a single high-energy ion can disrupt microelectronics. Long-duration exposure becomes a constant battle against entropy at the atomic scale. Now imagine adding human passengers. The human body evolved under Earth's gravity and atmospheric shielding. Remove both, and multiple biological systems begin to degrade. Bone density decreases in microgravity. Muscle mass declines. Radiation exposure increases cancer risk significantly over time. Psychological effects emerge from isolation, delayed communication, and sensory deprivation. But deep space adds something more subtle: temporal disconnection. Astronauts traveling at relativistic speeds would experience time differently from those left behind. They would effectively become time travelers into the future of their origin civilization. A journey of a few decades could mean centuries passing on Earth. When they return, if they return, they would find a universe that has moved on without them. Cities changed, civilizations altered, possibly nothing familiar remaining. And this is only interstellar travel within a single galaxy. Now expand further. Intergalactic travel is almost entirely beyond plausible physics. The distance between galaxies is measured in millions of light years. Even traveling at near light speed, the energy requirements and time scales become cosmological. Moreover, cosmic expansion accelerates separation. Some galaxies are already receding faster than light relative to us due to metric expansion. This means certain destinations are not just far, they are unreachable in principle. No ship, no signal, no particle can ever reach them once they cross the cosmic horizon. So deep space travel has a hard boundary imposed by cosmology itself. Not engineering, not biology, but the structure of space-time. Now consider the most extreme theoretical concept: generation ships, massive spacecraft designed to sustain human populations over thousands or millions of years, self-contained ecosystems drifting through interstellar space. These ships are not vehicles. They are artificial worlds, They require closed-loop life support systems, atmospheric recycling, water regeneration, agricultural biomes, genetic diversity maintenance, social and cultural stability over generational timescales. But even these face fundamental instability. Entropy accumulates in closed systems. Mechanical failures compound over time. Biological evolution may diverge from original populations. Cultural drift becomes inevitable. A generation ship is not a stable vessel. It is a slowly evolving ecosystem moving through emptiness. And even if it succeeds, its destination may no longer exist in the same form due to stellar motion and cosmic expansion. Now move even further into theoretical propulsion. Alcubierre warp drive concept suggests space-time manipulation, where a bubble of space contracts in front of a vessel and expands behind it. This would theoretically allow effective faster-than-light travel without locally breaking relativity. However, this requires exotic negative energy densities, conditions not known to be physically achievable at macroscopic scales. Quantum field theory allows negative energy in limited contexts, such as Casimir effect, but not in the quantities required for space-time engineering. So again, deep space resists traversal not by lack of imagination, but by constraint of physical law. And as you drift further into this conceptual abyss of travel limitation, you begin to realize something fundamental. Deep space is not just far away. It is structurally resistant to connection. Every layer of physics reinforces separation. Gravity binds locally. Expansion separates globally. Relativity limits speed. Thermodynamics limits energy. Quantum mechanics introduces uncertainty, and cosmology defines horizons. Together, they form a universe where movement is possible, but reunion is not guaranteed, where exploration is possible, but only within shrinking bounds of causality. And as you continue drifting through this immense structure of limitation and distance, past the last feasible trajectories of human spacecraft, past the last gravitationally bound regions of galaxies, slowly becoming isolated, islands in expanding space, we begin to encounter even deeper questions about what travel itself means, in a universe where destinations may no longer remain reachable, even in principle. As we move forward into the next layer of deep space, where motion itself begins to lose meaning against the backdrop of cosmic expansion and absolute isolation, where even the idea of arriving somewhere starts to break down under the combined pressure of relativity, expansion, and the sheer geometric structure of an evolving universe. Because at the deepest level, space travel is not only about crossing distance, it is about surviving time while distance keeps changing underneath you. In deep space, trajectories are not fixed. They are curved by gravity, stretched by expansion, and subtly perturbed by every mass concentration along the way. A spacecraft moving through interstellar space is not traveling in a straight line in any absolute sense. It is following a geodesic, the straightest possible path in curved space-time. But space-time itself is not static. It evolves. This means every interstellar journey is inherently non-permanent in its geometry. The path you calculate today will not be identical to the path you would calculate thousands of years later. Because the gravitational landscape shifts as stars move, galaxies rotate, and dark matter halos slowly evolve. Now consider propulsion again, but at the deepest physical limit, momentum exchange. All known spacecraft propulsion relies on conservation of momentum. You push mass backward to move forward. But in deep space, reaction mass becomes the central problem. To accelerate to even a fraction of light speed, a spacecraft must either carry enormous amounts of fuel or find external sources of momentum exchange. This is where theoretical concepts like interstellar medium scooping become important. A Bussard ramjet, for example, attempts to collect hydrogen from space using magnetic fields, then fuse it for propulsion. But interstellar hydrogen density is extremely low. On average, about 0.1 to 1 atom per cubic centimeter in relatively dense regions, and far less in voids. This means the collection area required becomes astronomically large, and drag effects begin to counteract thrust at higher speeds. In practice, the ship begins to fight the very medium it is trying to use. Now consider another approach: beamed propulsion. Instead of carrying fuel, a civilization could project energy across space using lasers or microwave arrays, pushing lightweight sails attached to spacecraft. This concept works in physics, but only if you already have massive infrastructure built across astronomical distances, and beam divergence over interstellar scales becomes a major limitation. Even small angular spread causes energy to disperse over vast areas, dramatically reducing efficiency at distance. So the further you go, the weaker your propulsion becomes unless the entire galaxy is engineered to support you. And this leads to a profound realization. Interstellar travel is not just a ship problem, it is a civilization scale problem. Now shift into relativistic travel again, because this is where deep space becomes truly counterintuitive. At high velocities, space and time begin to exchange roles in measurable ways. Length contraction occurs in the direction of motion. Distances shrink for the traveler, but not for the outside universe. So, from the perspective of a spacecraft approaching light speed, interstellar distances contract dramatically. However, this does not eliminate energy requirements. It only changes the observer's frame of reference. To an external observer, the ship still takes decades or centuries to cross space. To the traveler, the universe itself seems compressed. But the key limitation remains: acceleration. Because reaching relativistic speeds requires sustained energy input over time, and every additional percentage closer to light speed requires exponentially more energy than the last. This is not a linear problem, it is asymptotic. Now consider the biological implications again, but in deeper space terms. At relativistic speeds, even interstellar hydrogen becomes high-energy radiation relative to the ship. Particles that would normally be harmless become lethal due to kinetic energy in the ship's frame of reference. This means shielding becomes not just protective, but structural. Whipple shielding, magnetic deflection fields, layered composites, all become necessary just to survive interstellar dust impacts at relativistic velocities. Even tiny grains of dust become high-energy projectiles capable of damaging hull integrity. At 0.9 C, a grain of sand carries energy comparable to a small explosive device. So deep space is not empty in a benign sense. It is dynamically hostile at high speeds. Now expand outward again. Interstellar navigation must also account for gravitational lensing. Massive objects bend light, meaning that distant stars are not always where they appear to be. Light paths curve through space-time, creating distortions in perceived position. A spacecraft relying on optical navigation must constantly correct for relativistic light travel effects and gravitational deflections. Even pulsars, often proposed as natural navigation beacons, drift over time due to spin-down and galactic motion. So navigation in deep space becomes an ongoing problem of prediction rather than observation. You are not simply locating where things are, you are estimating where they were when their light began traveling toward you. adjusted for every gravitational field it passed through. Now consider time itself again, but from mission design perspective. Any interstellar mission must solve the multi-generation problem, because no single human lifetime can encompass meaningful interstellar travel under known physics without relativistic extremes. So missions must either suspend biological aging, cryogenic, or other hypothetical methods, or rely on generational succession, or use autonomous artificial intelligence systems. Each option introduces instability. Cryogenic suspension is not yet viable at long-term preservation scales without cellular damage. Generation ships introduce cultural and informational drift. AI systems introduce autonomy and potential divergence from original mission parameters. So even before a spacecraft leaves the solar system, its success probability begins to degrade based on time alone. Now zoom out further. At the edge of interstellar space lies the heliopause, the boundary where the solar wind from the sun is no longer strong enough to push against the interstellar medium. This is not a physical wall. It is a plasma boundary shaped by competing particle flows. Voyager 1 crossed this boundary after decades of travel, entering interstellar space for the first time in human history. But even here, deep space has only just begun. Beyond the heliosphere, the spacecraft is exposed to full galactic conditions. Cosmic rays intensify, magnetic fields become weaker and more turbulent, particle density becomes extremely low but energetic, and every kilometer traveled now takes significantly longer communication time until eventually signals become so delayed that mission control effectively becomes historical record rather than operational control. Now expand beyond the galaxy itself. Even if a spacecraft could cross the Milky Way, about 100,000 light-years in diameter, it would require timescales far beyond civilization stability under known conditions. Galactic rotation means that by the time a spacecraft crosses such distances, the galaxy itself has significantly reshaped its structure. Spiral arms shift, stars migrate, gravitational interactions alter orbits. So the destination is not only far away, it is dynamically different upon arrival. Now consider the ultimate deep space reality. On the largest scales, galaxy clusters are bound together by gravity. But even these are slowly being pulled apart by dark energy expansion. Over tens of billions of years, even galaxy clusters will become isolated cosmic archipelagos, each cluster containing its own gravitationally bound galaxies, drifting alone in an expanding universe. Beyond that, no new structures form. Space travel between these clusters becomes not just difficult, but cosmologically forbidden in many cases due to accelerating expansion. The metric expansion of space ensures that some regions move away faster than light can traverse the gap. So there exists a class of destinations that are physically real, but causally unreachable forever. Now imagine a spacecraft attempting to travel outward at this stage of cosmic evolution. It is not simply fighting distance. It is fighting the expansion of space itself. Even at maximum possible speed, the destination recedes faster than approach can compensate. This is not a failure of propulsion. It is a property of space-time geometry, and so the universe introduces a final limitation to travel. Not fuel, not engineering, not biology, but causality, the structure of what can influence what. And as you continue drifting deeper into this realization, past the last reachable stars of any gravitationally bound system, past the last feasible trajectories of interstellar navigation, past the limits imposed by energy, radiation, and relativistic geometry, we begin to approach regions where even the concept of a journey becomes undefined. under cosmological expansion laws, where movement through space no longer guarantees change in relation to destination, and where deep space begins to reveal yet another layer of constraint that governs not just travel itself, but the very possibility of reaching anything beyond the next horizon of expanding emptiness, where even the simplest requirement for survival, something as ordinary on Earth as eating, becomes a profound engineering and thermodynamic problem when placed against the backdrop of deep space. Because food in deep space is not just nutrition, it is energy storage, it is mass budgeting, it is entropy management inside a sealed, isolated system with no external replenishment. On Earth, food chains are open systems. Energy flows continuously from the sun into plants via photosynthesis, then into animals, then into humans, and is constantly replenished. In deep space travel, that chain is cut completely. There is no sunlight strong enough for meaningful agricultural output beyond the inner solar system unless enormous artificial light systems are built. There is no soil cycle unless fully synthetic hydroponic or aeroponic systems are used. There is no external ecological input. Everything must be closed loop. This creates one of the hardest constraints in all of space travel: mass energy recycling efficiency. In a spacecraft traveling through deep space, every gram of matter must be accounted for. Food is not consumed in the Earth sense, it is transformed. Carbon, hydrogen, oxygen, nitrogen, CHON elements must be continuously cycled through biological and mechanical systems. Plants or algae convert energy into biomass. Humans consume biomass. Waste products must be broken down again into usable nutrients. Any inefficiency in this loop results in gradual system collapse. Now consider caloric requirements. A human at rest requires roughly 2,000 to 3,000 kilocalories per day, depending on activity and environment. In space, energy expenditure can increase due to microgravity adaptation stress, radiation repair processes, and environmental control systems. Multiply that by a crew of hundreds or thousands over decades or generations, and the mass requirements become enormous. Food is not just sustenance, it becomes a logistical constraint comparable to fuel. Now imagine a generation ship, a vessel designed to travel for centuries or millennia through interstellar space. Food systems on board must operate like miniature biospheres. The most realistic candidates are hydroponic agriculture systems, algae bioreactors, spirulina, chlorella-type organisms, insect protein farming systems, synthetic biology production of protein analogues, microbial fermentation vats producing fats and amino acids. Each system has trade-offs. Hydroponics is stable but space inefficient. Algae systems are efficient but limited in dietary diversity. Insect farming is high protein but psychologically difficult for some populations. Synthetic biology is flexible but technologically fragile. And all of them depend on one thing: energy input. Without continuous energy likely from nuclear reactors in deep space, none of these systems can sustain long-term production. So food in deep space is fundamentally a conversion problem. Energy, biomass, human metabolism, waste energy cycle again. But unlike Earth, there is no external correction if the cycle becomes inefficient. Even a 1% loss per cycle becomes catastrophic over hundreds of iterations. Now consider storage. Food storage in deep space cannot rely on traditional methods like refrigeration alone. Systems must be redundant across multiple preservation modes: freeze-drying, radiation sterilization, vacuum sealing, chemically stabilized nutrient blocks, biological preservation in dormant seed banks. But storage introduces another problem: degradation over time. Radiation in deep space slowly breaks molecular bonds. Cosmic rays can alter stored organic compounds. Even shielding cannot eliminate all high-energy particle interactions over long durations. So stored food is not truly permanent. It is slowly decaying even when unused. Now expand the scale again. In long-duration missions, food is not just consumed. It is scheduled like a mission-critical resource. Every calorie is mapped to trajectory energy, psychological stability, and biological maintenance. Crew members become part of an integrated system where metabolism is accounted for in engineering models. Human bodies are effectively energy processing units inside a closed spacecraft economy. Now introduce another deep space factor, microgravity. In low or zero gravity environments, biological systems behave differently. Fluid distribution changes. Bone density decreases. Muscle atrophy occurs. Digestive efficiency can shift. This directly affects nutritional requirements. Food must not only provide energy, but counteract physiological degradation. This means higher protein ratios, increased calcium and vitamin D analogs, carefully controlled electrolyte balance. Even taste becomes a scientific problem. In microgravity, fluid shifts reduce olfactory sensitivity. Food must be more strongly flavored to maintain psychological satisfaction. Otherwise, appetite suppression leads to nutritional deficiency cycles. So food becomes both biochemical and psychological engineering. Now extend further into deep space isolation. One of the most critical hidden constraints is psychological monotony. In deep space missions lasting years or generations, food becomes one of the only recurring sensory experiences. This leads to a requirement for variety in texture, flavor, and presentation, even when ingredients are limited. But variety requires additional biological diversity systems, which increase complexity and failure risk. So engineers face a trade-off: stability versus psychological health. Now consider failure modes. If food systems degrade even slightly in deep space, there is no external rescue, no supply chain, no resupply mission. Every inefficiency compounds over time. A small microbial contamination event in a closed hydroponic system can propagate through the entire food chain. A nutrient imbalance can cascade into population-wide deficiencies. A reactor failure can collapse agricultural output entirely. In deep space, food systems are not just important, they are existential. Now zoom out further. The ultimate food problem in deep space is not production. It is sustainability under isolation, because every system must operate without external input for durations that exceed normal human historical scales. And the longer the journey, the more fragile the system becomes due to entropy accumulation. Even AI-managed agricultural systems would face hardware degradation over centuries. Sensors drift, actuators wear down, biological systems evolve or mutate unexpectedly. Nothing remains perfectly stable in a closed system indefinitely. Now consider relativistic food effects again. At near light speeds, time dilation means that onboard time passes more slowly relative to external universe time. This theoretically reduces perceived food consumption over external timescales, but does not reduce internal metabolic requirements. So from the crew's perspective, food consumption remains unchanged. From the universe's perspective, their journey appears compressed. But the engineering challenge remains identical: sustain biological life continuously without interruption. Now consider interstellar colonization attempts. Every colony ship must carry not just food, but full ecological reconstruction capability. Because once it arrives, it may need to bootstrap an entire biosphere from scratch. That means carrying seed banks, microbial diversity libraries, synthetic soil systems, nutrient cycling reactors. Atmospheric processing systems. Food is no longer a product, it is an ecosystem output. And even then, success is not guaranteed. Because planetary conditions may not match expectations, soil chemistry may differ, atmosphere may be toxic, gravity may alter biological function. Food systems must adapt in real time to unknown environments after arrival. Now return to deep space itself. As ships travel farther from any star, external energy input declines towards zero. This forces reliance on onboard nuclear reactors or hypothetical fusion systems for indefinite durations. But even fusion fuel is finite unless carefully bred or harvested. So, every gram of fuel is also part of the food economy indirectly, because energy limits define agricultural capacity. Food and propulsion become linked systems in deep space architecture. If propulsion efficiency drops, energy for food production drops. If food production fails, human maintenance fails. If humans fail, system oversight fails. It is a tightly coupled survival loop. And now consider the most extreme scenario. A spacecraft drifting through intergalactic voids, where no resupply is possible for millions of years, relying entirely on self-sustaining, closed ecological cycles, powered by slowly degrading energy systems. Maintaining biological life under radiation exposure and metabolic constraints while traversing distances so large that even light itself takes millions of years to cross them. In such a scenario, food is not just survival. It is a continuously maintained equilibrium between life and entropy, a balance that must be preserved without interruption across time spans that dwarf entire planetary histories, while the ship continues moving through regions where even atoms are separated by light years of distance, and where the next potential source of raw material may not exist in any reachable direction, as the system continues operating in isolation against the expanding structure of the universe itself. And as we move further into the next layer of deep space, where even long-term ecological stability begins to encounter limits imposed by physics, time, and cosmic separation that continue to grow without end, where even the food systems, already stretched into fragile closed loops of biological and chemical recycling, ultimately collapse into a deeper, more fundamental constraint that governs everything in deep space travel: energy. Because in deep space, energy is not just another requirement. It is the root requirement from which every other system emerges. Food production needs energy. Air recycling needs energy. Water purification needs energy. Temperature control needs energy. Radiation shielding systems need energy fields or active cooling. Even computation and navigation depend on continuous energy input. Without energy, a spacecraft is not a vessel. It is a drifting dead mass. And unlike food or materials, energy cannot simply be stored indefinitely without losses or constraints. In classical physics, energy is conserved. But in engineering reality, usable energy degrades into unusable forms through entropy. This is the core problem of deep space energy systems. Not how much energy exists, but how much usable energy can be maintained over time in isolation. Now begin with the most basic deep space energy source: chemical energy. On Earth, chemical fuels dominate civilization: hydrocarbons, batteries, combustion systems. But chemical energy density is extremely low compared to the demands of space travel. And more importantly, it is finite. Once consumed, it does not regenerate in a closed system without external input. So chemical energy becomes almost irrelevant beyond short-duration missions. Now move to nuclear fission. Fission reactors are currently the backbone of theoretical deep space propulsion and habitat energy systems. They provide extremely high energy density compared to chemical sources. They can operate for years or decades depending on fuel supply. But fission still relies on finite isotopes like uranium or plutonium. Once fuel rods are exhausted, the system requires resupply or breeding cycles. Breeder reactors can extend this significantly by converting fertile material into fissile fuel. But even this process is limited by initial material mass. So fission is powerful, but not infinite. Now move deeper. Nuclear fusion. Fusion represents the most promising near-term deep space energy source. It mimics stellar processes, fusing hydrogen isotopes into helium and releasing enormous energy. In principle, fusion fuel like deuterium can be extracted from water or interstellar hydrogen. But in practice, confinement, ignition stability, and net energy gain remain unsolved at large scale for continuous autonomous systems. Even if fusion becomes fully functional, it still requires fuel input and extremely precise engineering conditions. And, in deep space, maintaining stable fusion reactors over centuries introduces cumulative mechanical and material degradation risks. Now consider antimatter. Antimatter annihilation offers the highest energy density known in physics. Matter-antimatter conversion yields nearly 100% mass-energy conversion efficiency via E equals mc squared. But antimatter production requires enormous energy input. Storage is extremely unstable due to annihilation risk with normal matter. And even nanogram-scale containment systems require advanced electromagnetic traps with near-perfect vacuum conditions. So, antimatter is theoretically ideal, but practically fragile and resource-intensive. Now step further into deep space reality. Solar energy. Close to stars, solar energy is abundant and reliable, but energy flux decreases with the square of distance. At Earth orbit, 1,361 watts per square meter. At Jupiter, 50 watts per square meter. At interstellar distances, effectively negligible. Beyond the heliopause, solar panels become almost useless unless they are unimaginably large. So deep space travel quickly loses access to its simplest energy source. Now consider gravitational energy harvesting. In theory, spacecraft could use gravitational assists to extract energy from orbital mechanics. Slingshot maneuvers around planets or stars can increase velocity without fuel consumption. But this does not generate net energy. It only redistributes existing orbital momentum. Once a ship leaves planetary systems, this option disappears. Now, we reach a more exotic concept: beamed energy infrastructure. A civilization could construct massive laser or microwave arrays to transmit energy across space. Spacecraft would receive energy remotely, eliminating onboard fuel constraints. However, beam divergence becomes a critical limitation over interstellar distances. Even with precise focusing, diffraction spreads energy over vast areas, and maintaining alignment across light years requires extreme precision and real-time correction, accounting for stellar motion and relativistic effects. This effectively means deep space energy beaming requires a galaxy-scale infrastructure network. Now consider the most fundamental deep space constraint: energy density versus time. Every energy system suffers degradation. Reactor materials weaken under radiation. Superconductors lose efficiency under cosmic ray bombardment. Batteries degrade chemically over cycles. Thermal systems lose efficiency through entropy accumulation. Mechanical systems wear down over time. So, even if energy is initially abundant, system efficiency declines continuously. This leads to a slow but unavoidable reduction in usable energy output over mission duration. Now introduce the concept of power budgeting in deep space missions. Every spacecraft must allocate energy across competing systems: propulsion, life support, computation, communication, radiation shielding, thermal regulation, food production systems. These systems are not independent. They compete for the same limited energy reservoir. Increasing one reduces capacity in another. For example, more propulsion power reduces available energy for agriculture systems. More shielding reduces energy available for communication. More life support redundancy increases mass, increasing propulsion energy requirements. This creates a multivariable optimization problem with no perfect solution. Now expand further into relativistic deep space travel energy constraints. At high velocities, kinetic energy increases according to relativistic equations. As velocity approaches light speed, required energy approaches infinity. This means that the most energy-intensive part of interstellar travel is not cruising. It is acceleration and deceleration. Deceleration is especially critical, because arriving at a destination at relativistic speed without the ability to slow down results in catastrophic pass-through events. So a spacecraft must carry energy not only to accelerate, but to stop, doubling energy requirements in practical mission design. Now consider energy leakage in deep space systems. Even in perfectly insulated systems, energy is lost. Heat radiates into space. Electronics dissipate waste heat. Radiation escapes containment. Quantum processes introduce minimal energy fluctuations. In a vacuum, heat rejection is only possible via infrared radiation. There is no air to carry heat away. Radiators must emit photons to shed thermal energy. This makes thermal control a major energy sink in deep space engineering. Large radiative panels are required, but larger systems increase vulnerability to micrometeorite impacts and radiation damage. Now move to the ultimate energy problem: entropy. Every energy conversion process increases entropy. Even the most efficient systems cannot avoid waste heat production. In deep space, waste heat is particularly problematic because it is difficult to dissipate efficiently without massive radiative structures. So energy systems become increasingly inefficient over time unless continuously maintained or repaired. Now consider system-wide failure modes. A small reduction in energy output does not simply reduce performance. It cascades through dependent systems. Less energy, weaker life support, reduced biological efficiency, reduced crew performance, reduced maintenance capability, further energy degradation. This is a feedback loop towards systemic collapse. Now, expand to interstellar scale energy economics. A civilization attempting deep space expansion must allocate energy not just per ship, but per entire network of missions. Energy becomes the limiting currency of expansion, not space, not matter, energy availability. Even galaxies contain vast amounts of matter, but usable energy extraction is constrained by thermodynamic efficiency and entropy production limits. Now extend to cosmological scale. As the universe expands and dark energy dominates, usable energy density decreases over time. Stars burn out, radiation redshifts, matter becomes more isolated, black holes slowly evaporate. The total accessible energy per unit volume declines. This leads to a universe where energy exists, but becomes increasingly unusable, a state sometimes associated with the concept of heat death. Not absence of energy, but absence of energy gradients. No differences in temperature, no exploitable potential, no flow. Now return to deep space travel itself. Even if a spacecraft could somehow solve propulsion, food, navigation, and shielding, it would still face the ultimate constraint: energy continuity over time. Because deep space travel is not a single event, it is a continuous maintenance of existence in a hostile thermodynamic environment. Every second requires energy input. Every system depends on uninterrupted power flow. Any disruption, even brief, can cascade into irreversible system failure. And as we move deeper into this understanding, past nuclear, chemical, and relativistic limits, past beamed energy and gravitational assists, past all known engineering frameworks, we begin to approach a region where energy itself is no longer simply a resource to be harvested or stored, but a diminishing gradient across expanding spacetime where every possible source becomes increasingly isolated and diluted, and where deep space travel transforms from a problem of propulsion into a problem of sustaining ordered systems against the universal trend toward equilibrium. As we continue further into the next layer, where even the concept of usable power begins to break down under cosmological expansion, and the limits imposed by entropy across the structure of the universe itself, where even energy, already strained by distance, inefficiency, and entropy, is no longer the only silent threat in deep space travel, because another phenomenon permeates the interstellar void with equal inevitability and far more direct physical damage to both machines and biology: radiation. Unlike food or energy, radiation is not something that is consumed, stored, or carefully budgeted. It is something that continuously enters the system from outside, whether you want it or not. And in deep space, there is no atmosphere to absorb it, no magnetosphere to deflect it, no planetary shielding, only raw exposure to the high-energy environment of the galaxy and beyond. To understand the radiation problem in deep space, we must begin with its sources. The first and most constant is the galactic cosmic ray background. These are high-energy particles, primarily protons, helium nuclei, and heavier atomic nuclei, accelerated to near light speeds by extreme astrophysical events, supernova explosions, neutron star collisions, black hole accretion shocks, relativistic jets from active galactic nuclei. Each of these processes injects particles into the galaxy with energies far beyond anything human technology can currently reproduce at scale. When these particles enter deep space, they travel in straight lines until they collide with matter. And in interstellar space, matter is sparse enough that many of them travel for thousands or millions of years before interacting. This creates a persistent, omnidirectional radiation field throughout the galaxy. Now consider what happens when this radiation reaches a spacecraft. Unlike light, which can be reflected or absorbed with relative ease, high-energy cosmic rays penetrate deeply into materials. They pass through hulls, electronics, and biological tissue, depositing energy along their path in concentrated bursts. This is not gentle heating, it is ionization damage. At the atomic level, cosmic rays strip electrons from molecules, breaking chemical bonds and creating reactive ions. In biological systems, this leads to DNA strand breaks, protein damage, and cellular dysfunction. In electronics, it causes bit flips, circuit degradation, and long-term material fatigue. Now, consider that this happens continuously in deep space. Every second, every hour, every year, there is no pause. Now, expand the problem further. Cosmic rays are not uniform in intensity. They vary depending on location in the galaxy, solar activity, and shielding conditions. Inside a planetary magnetosphere like Earth's, most of this radiation is deflected or trapped in radiation belts, such as the Van Allen belts. But once a spacecraft leaves this protective bubble, it enters the full interstellar radiation field. This is the true deep space environment. And here, radiation exposure increases dramatically compared to low Earth orbit conditions. Now consider secondary radiation. When high-energy cosmic rays strike spacecraft hull materials, they do not simply stop, they produce particle showers. A single high-energy proton can collide with atoms in shielding material, generating secondary particles, neutrons, pions, gamma rays, muons, electron-positron pairs. This means that shielding against radiation is not simply a matter of blocking particles. It becomes a problem of managing cascades of particle interactions inside the shielding itself. Thicker shielding is not always better, because it can generate more secondary radiation internally. Now consider biological exposure in deep space missions. Humans are particularly sensitive to ionizing radiation because of cellular replication systems. Bone marrow, gastrointestinal lining, and reproductive cells are especially vulnerable. Chronic exposure leads to increased cancer risk, tissue degeneration, and potential long-term genetic instability. In deep space travel scenarios lasting years or decades, radiation dose accumulation becomes one of the primary limiting factors for crew survivability. Even low-dose rates become dangerous over long durations. Now expand to spacecraft electronics. Modern spacecraft rely heavily on semiconductor technology, but semiconductors are highly sensitive to radiation-induced errors. Single event upsets, CEUs, occur when a charged particle passes through a microchip and alters stored data. This can cause memory corruption, system resets, or control logic failures. To mitigate this, engineers use radiation-hardened components, redundant systems, error-correcting codes, shielding layers, fault-tolerant architectures. But all of these add mass, complexity, and energy cost. Now consider long-duration deep space missions. Over time, radiation damage accumulates in materials themselves. Metals become embrittled, polymers degrade. Optical systems become clouded. Solar cells lose efficiency due to lattice damage. Even structural components slowly degrade under constant particle bombardment. This is not catastrophic failure in a single event. It is gradual systemic erosion. Now move beyond galactic cosmic rays to another major radiation source: solar particle events. Within stellar systems, stars occasionally emit massive bursts of charged particles during solar flares and coronal mass ejections. These events can produce intense radiation storms that overwhelm spacecraft systems if unshielded. In interplanetary space, this is a major hazard, but in deep interstellar space, it becomes less relevant due to distance from active stars. However, it is replaced by a more uniform hazard: isotropic cosmic radiation. Now, introduce an even more subtle radiation source: the diffuse gamma-ray background. This is a faint, omnipresent radiation field generated by countless unresolved astrophysical sources across the universe. Active galactic nuclei, pulsars, and exotic high-energy processes contribute to a persistent gamma-ray glow across the sky. It is extremely weak compared to localized sources, but non-zero everywhere, meaning deep space is never truly radiation-free. Now consider the most fundamental radiation source of all: the early universe itself. The cosmic microwave background is the afterglow of recombination. But at earlier times in cosmic history, radiation density was far higher. Today it is diluted and redshifted into microwaves, but still contributes a uniform low-energy photon bath throughout space. While not harmful biologically, it is a reminder that the universe itself is filled with residual radiation from its origin. Now expand into shielding physics. To protect against radiation in deep space, spacecraft must rely on mass shielding or active field shielding. Mass shielding uses dense materials like water, polyethylene, or specialized composites rich in hydrogen to absorb and slow charged particles. Hydrogen-rich materials are particularly effective because they reduce secondary neutron production compared to heavy metals. However, mass shielding increases spacecraft weight, which increases propulsion energy requirements, which increases mission cost exponentially. Active shielding concepts involve magnetic or electric fields designed to deflect charged particles away from the spacecraft. But generating strong enough fields over large volumes requires enormous power and advanced superconducting systems. And even then, neutral particles like gamma rays and neutrons are extremely difficult to deflect, so no shielding system is perfect. Now consider the radiation gradient in deep space. Radiation is not uniform everywhere. Near supernova remnants, it is extremely intense. Near star-forming regions, elevated. In interstellar voids, lower but still present. Near black holes, highly variable depending on accretion activity. This means spacecraft trajectory planning must consider not only gravitational and energy constraints, but also radiation exposure mapping across interstellar routes. Now expand into relativistic radiation effects. At high velocities, radiation becomes even more dangerous due to relativistic aberration. Particles and photons in the direction of travel become blue-shifted in energy. This increases their effective radiation dose in the spacecraft frame. So, a spacecraft moving at relativistic speeds through interstellar space does not simply experience normal cosmic radiation. It experiences intensified forward-facing radiation flux. This creates a directional hazard that grows with velocity. The faster you go, the more dangerous the incoming radiation becomes. Now consider long-term mission implications. Radiation is cumulative and irreversible in biological systems. Damage accumulates over time. Repair mechanisms exist, but are not perfect. Beyond certain thresholds, system failure becomes statistically inevitable without mitigation. So deep space travel requires not just shielding, but lifespan modeling under radiation exposure constraints. Now expand to interstellar dust interactions. Even tiny dust grains, though sparse, become radiation amplifiers at high-speed impacts. When a high-velocity dust particle strikes a shield, it produces plasma, X-rays, and particle showers. This creates localized radiation bursts inside the shielding system. So radiation in deep space is not only external, it is also internally generated by interaction with matter. Now step back and observe the full picture. Deep space radiation is a layered system. Constant, galactic, cosmic ray background, diffuse gamma ray field, solar particle events within systems, secondary radiation from shielding interactions, relativistic radiation amplification, material degradation-induced emissions over time. It is not a single hazard. It is a continuous environmental condition of space itself, and it cannot be eliminated, only managed. Now combine this with all previous constraints. Food systems degrade under radiation. Energy systems degrade under radiation. Electronics degrade under radiation. Biological systems degrade under radiation. Radiation becomes the universal stress factor, acting on every subsystem of deep space travel simultaneously. It does not compete with other problems. It amplifies them. And as you drift further into the interstellar darkness, beyond the heliosphere, beyond stellar influence, beyond dense galactic regions, into the vast, low-density plasma of the intergalactic medium, where particles drift for millions of years under faint gravitational fields and weak background radiation fields that persist since the early universe, we begin to encounter regions where even radiation itself becomes the dominant physical interaction, shaping the survivability of matter and technology over cosmic timescales. as every structure slowly experiences cumulative energetic bombardment from the universe's most energetic remnants while moving through expanding space-time that continues to stretch distances beyond the reach of even the most advanced propulsion concepts. And we continue forward into the next layer, where radiation, energy loss, and isolation begin to merge into a single unified constraint, governing the fate of any object attempting to move through deep space at all. Where even radiation and energy, already stretched into fragile balances across expanding space-time, begin to converge into a deeper limitation that governs all motion, all systems, and all attempts at survival in the universe. Time. Because in deep space travel, time is not just a background parameter. It is the dominant physical constraint that cannot be engineered away. Unlike energy, which can be stored or converted, or radiation, which can be partially shielded, time is not something a spacecraft can control. It flows according to relativity, expansion, gravity, and motion. And in deep space, these effects become extreme. The first layer of the time problem is simple classical delay. Light has a finite speed, approximately 299,792,458 meters per second. This means that every observation, every communication, every navigation signal is fundamentally delayed. At Earth-Moon distance, this delay is seconds. At Mars, minutes. At the outer solar system, hours. But in interstellar space, delays become years, decades, centuries. A signal sent from a spacecraft near another star is not communication in real time. It is historical transmission. You are not talking to the present. You are talking to the past. Now expand this further into relativistic time. According to Einstein's theory of special relativity, time is not absolute. It depends on velocity and gravitational potential. As a spacecraft approaches relativistic speeds, time dilation becomes significant. The formula governing this is gamma equals 1 square root 1 minus v squared divided by c squared, where gamma increases rapidly as velocity v approaches the speed of light c. At 0, 9 c, time slows noticeably. At 0, 99 c, time slows dramatically. At 0, 999 c, time nearly freezes relative to external observers. This creates one of the most paradoxical effects in deep space travel. The traveler and the universe experience time differently. From the spacecraft's perspective, a journey of decades may feel like only a few years. From the external universe's perspective, centuries or millennia may pass. So deep space travel becomes a form of asymmetric time experience. You leave one epoch of the universe and arrive in another. Now consider acceleration phases. Time dilation does not only affect cruising speed, it accumulates over the entire trajectory. Acceleration, deceleration, and coasting all contribute differently depending on reference frame. This makes mission planning a relativistic problem, not a classical one. Trajectory design is no longer just about distance. It becomes about world line optimization in space-time geometry. Now expand to gravitational time dilation. Time also flows differently in gravitational fields. Near massive objects like neutron stars or black holes, time slows relative to regions of weak gravity. This is not theoretical. It has been measured using atomic clocks on Earth at different altitudes. In deep space missions that pass near massive bodies for gravitational assists, onboard time can diverge slightly from external cosmic time. Now combine both effects. A spacecraft moving at relativistic speeds near strong gravitational fields experiences compounded time distortion. This creates complex temporal asymmetries across mission phases. Now expand further into the most unsettling consequence of deep space time travel: causal disconnection. As distance increases, light travel time increases. As expansion accelerates, regions of space move beyond causal contact. This creates cosmological horizons, boundaries beyond which events can no longer affect each other, even in principle. So time in deep space is not only delayed, it becomes partitioned. Different regions of the universe evolve independently after separation. Now consider long-duration missions. A spacecraft traveling for thousands of years in its own frame may return to find that millions or even billions of years have passed externally due to relativistic or cosmological effects. This is not science fiction. It is a direct consequence of relativistic spacetime geometry. Now introduce another layer: entropy and time direction. The arrow of time is defined by entropy increase. In deep space, entropy continues to increase globally, even if locally isolated systems maintain order. This means that while a spacecraft maintains internal structure, the universe outside continues evolving toward higher entropy states. Stars burn out, galaxies disperse, black holes evaporate. Time, in this sense, is not just passing. It is changing the structure of everything outside the ship. Now expand to communication lag as temporal separation. In deep space missions, communication is not interactive. It becomes archival. Messages sent between Earth and interstellar spacecraft represent different temporal layers of civilization. A reply is not dialogue. It is delayed history. This creates psychological and operational isolation, where decision-making must be fully autonomous for long periods. Now consider the deepest time problem: cosmological time, evolution. The universe itself changes over time scales far beyond human comprehension. Star formation rates decline, galaxy clusters evolve, dark energy drives accelerated expansion, background radiation cools as space stretches, so the same location in space does not remain the same in time. Space and time together form a dynamic, evolving system. Now introduce the concept of future cosmic isolation. As expansion continues, distant galaxies will cross beyond the cosmic event horizon. After that point, no signal from them will ever reach us again. This means that future civilizations may see a progressively smaller observable universe. Time will not only separate events, it will erase access to regions of reality. Now combine all layers of the time problem. Signal delay makes communication asynchronous. Relativistic motion decouples experience time from external time. Gravitational fields distort local time flow. Cosmic expansion separates regions causally. Entropy defines a directional arrow of change. Cosmological evolution alters the structure of observable reality over time. Together, these effects mean that deep space travel is not just movement through distance. It is movement through multiple, diverging timelines of the universe itself. Now consider the extreme implication. Two observers separated by interstellar or intergalactic distances are not just far apart. They are temporally misaligned in their experience of cosmic history. Each exists in a partially independent slice of universal evolution. Now return to the spacecraft itself. Every system on board is time-dependent. Food cycles degrade over time. Energy systems decay over time. Radiation damage accumulates over time. Mechanical wear increases over time. Biological aging continues, unless altered by relativistic effects. Time is the variable that integrates all other deep space problems. It is the dimension in which all failures accumulate. Now expand further into mission design constraints. Every deep space mission must be engineered not only for distance, but for duration stability. The longer the mission, the more time-dependent risks accumulate exponentially. Probability of system failure increases. Redundancy systems degrade. Unexpected astrophysical events becomes statistically significant. Cumulative radiation exposure rises. Entropy increases in all closed systems. Time turns uncertainty into inevitability over long enough scales. Now consider the most extreme theoretical scenario: intergalactic travel. At these distances, even light takes millions of years to cross space. A spacecraft leaving one galaxy cluster may arrive in another when both clusters have evolved into completely different cosmic structures. The universe at departure is not the universe at arrival. Time has transformed the destination itself. Now expand to the ultimate time horizon. In the far future of an accelerating universe, cosmic expansion will isolate gravitationally bound systems into disconnected islands of matter, surrounded by an ever-growing darkness. Beyond that, even black holes will evaporate over immense timescales due to quantum effects. Eventually, the universe may approach a state where no thermodynamic gradients remain, a state where time continues mathematically, but no physical processes can meaningfully distinguish one moment from another. And as you drift further into this understanding of time in deep space, beyond relativistic motion, beyond cosmological horizons, beyond communication delays and entropy-driven decay, we begin to approach the next layer, where time itself is not just a passive dimension of motion, but the central limiting factor that determines whether any journey can ever complete in a universe where every destination evolves while it is being approached, and where even the act of traveling becomes inseparable from the irreversible unfolding of cosmic history itself, where every second of motion through deep space is also a second of irreversible separation from the point of origin, and where the concept of going back becomes less like a journey and more like a mathematical impossibility imposed by the structure of space-time itself. And in this framework, one of the most profound consequences of deep space travel emerges: the loss of contact with Earth. At first, it begins as something simple and almost harmless: a delay. When a spacecraft travels beyond the Moon, communication lag becomes noticeable. At Mars' distance, it becomes inconvenient. At the outer planets, it becomes operationally limiting. But as distance increases exponentially, this lag transforms into something fundamentally different. It becomes temporal disconnection, because communication in physics is limited by the speed of light. Nothing can carry information faster than approximately 299,792 kilometers per second. So every signal sent from Earth is already a message from the past, and every reply from deep space is equally delayed on its return. Now extend this to interstellar distances. At just 4.24 light-years away, the nearest star system, Proxima Centauri, imposes a minimum 4.24-year one-way communication delay. A full conversation cycle becomes nearly a decade long. This is not dialogue anymore. It is archival exchange between two separated timelines. Now imagine a spacecraft at 100 light-years, or 1,000, or 100,000. Each step deeper into space multiplies the delay linearly with distance, but the operational consequences grow non-linearly. Because missions are not single messages, they are continuous control systems, and control systems require feedback. When feedback is delayed by years or decades, real-time correction becomes impossible. So the spacecraft must increasingly operate autonomously. At this point, Earth is no longer a mission control center. It becomes a historical origin point. Instructions sent from Earth no longer reflect current conditions. They reflect conditions from years, decades, or centuries ago. Now expand this further into relativistic separation. If a spacecraft is traveling at relativistic speeds away from Earth, two effects combine. Increasing distance reduces signal speed due to travel time. Time dilation alters the rate at which onboard events occur relative to Earth. This creates asymmetric communication timelines. From Earth's perspective, The spacecraft appears to slow down in time as it approaches light speed. From the spacecraft's perspective, Earth appears to accelerate into the future. This leads to a strange asymmetry. Earth is not just far away. Earth becomes temporally ahead. Now introduce the concept of signal dilution. As signals travel through space, they spread out. Electromagnetic radiation intensity decreases with the square of distance. This is the inverse square law. I is proportional to 1 r squared. At interstellar distances, even powerful transmissions become extremely weak. By the time a signal reaches deep space probes at extreme distances, it is not only delayed, it is degraded, stretched, redshifted, diminished into background noise levels. Eventually, signals become indistinguishable from cosmic microwave background noise. At that point, communication is not just delayed, it becomes physically unrecoverable. Now consider cosmic expansion effects on communication. In an accelerating universe, space itself expands between distant regions. This causes redshift of photons and increasing separation velocity between objects not gravitationally bound. At sufficiently large distances, recession velocity exceeds the speed of light due to metric expansion. This does not violate relativity locally, but it has a devastating communication consequence. Signals emitted from such regions will never reach Earth, not because they are blocked, but because space expands faster than they can traverse. This creates a communication horizon, a boundary beyond which Earth is permanently unreachable from the spacecraft's position, or vice versa. Now expand into mission-scale consequences. As spacecraft travel deeper into space, communication becomes delayed, then intermittent, then degraded, then effectively lost, then physically impossible. This is not a gradual decline in quality. It is a phased transition in connectivity. At a certain threshold, Earth ceases to be a reachable node in the communication network of the spacecraft. Now consider onboard autonomy. Once contact with Earth becomes unreliable, spacecraft must transition to fully autonomous operation. This requires onboard systems capable of navigation without external correction, scientific decision-making without human input, self-repair protocols, adaptive mission planning, long-term error correction without external calibration. But autonomy introduces drift, because any closed system without external reference gradually diverges from its original baseline. Small computational errors accumulate. Environmental uncertainties compound. Decision trees evolve unpredictably over long time scales. So even autonomous systems slowly lose alignment with initial Earth-based mission intent. Now expand into psychological separation for human crews. For crewed deep space missions, loss of contact with Earth is not only technical, it is cognitive and emotional. Humans rely heavily on external social and cultural feedback loops. Earth is not just a communication partner, it is a psychological anchor. As communication delays increase, conversations become asynchronous. Emotional responses are delayed. Shared cultural context becomes outdated. Earth's reality becomes increasingly abstract. Eventually, Earth is no longer a lived reference point. It becomes a mythologized origin, a place known only through delayed messages and archived transmissions. Now consider generational time effects. In long-duration missions, crew members may be born and die aboard the spacecraft. For them, Earth is not a memory, it is inherited information. A generational ship may never experience direct contact with Earth after departure, only data fragments transmitted across centuries of delay. And as time dilation increases at relativistic speeds, the discrepancy becomes even more extreme. A crew traveling at near light speed might experience only a few years on board while centuries pass on Earth. From Earth's perspective, the ship disappears into deep space history. From the ship's perspective, Earth rapidly becomes a distant, fast-forwarding timeline. Now expand into complete signal isolation. At extreme distances, even communication beacons become ineffective. Photon scattering, redshift, and cosmic background noise degrade signals beyond recoverability. Eventually, the spacecraft may reach a region where Earth is no longer visible, Earth is no longer detectable. Earth's electromagnetic footprint has faded below cosmic background levels. At that point, Earth is not just unreachable, it is observationally erased from the spacecraft's sky. Now reverse the perspective. From Earth, the spacecraft also begins to disappear, first as a faint signal, then as a delayed transmission source, then as an unresolved point of data, then as a historical trajectory, then finally as a predicted path with no incoming updates. Eventually, Earth loses all real-time awareness of the spacecraft's state. Now consider the deepest layer of separation, causal disconnection. Once light travel time exceeds mission duration relevance, both Earth and spacecraft become causally decoupled systems. They may still exist in the same universe, but they no longer influence each other in any operational sense. Their shared timeline splits into independent branches of cosmic history. Now expand into intergalactic scale loss of contact. Between galaxies, even communication becomes constrained by expansion-driven horizons. Some regions of space are receding so rapidly that signals cannot bridge the gap even at light speed. This creates permanent communication isolation zones. Civilizations in different clusters cannot exchange information once separated beyond the cosmic horizon. So loss of contact is not just mission-specific. It is a fundamental property of cosmic structure. Now return to deep space travel itself. Every spacecraft leaving Earth is effectively entering a regime of increasing informational isolation. First seconds of delay, then minutes, then hours, then years, then centuries, then cosmological disconnection. Earth gradually transitions from home base to irretrievable origin point. And as we move further into this deep space reality, past relativistic effects, past energy constraints, past radiation hazards, past food system limitations, and past the increasingly severe separation of communication networks stretched across expanding space-time, we begin to approach the next layer, where even the concept of contact itself begins to dissolve into purely theoretical correlation between two systems that no longer share any practical channel of exchange. As the universe continues to expand, time continues to diverge, and deep space travel progresses into a state where Earth is not simply far away, but fundamentally detached from any possible interaction pathway that could ever reconnect it to the traveler again, where even Earth itself, already fading through time delay, relativistic separation, radiation noise, and cosmological horizons, becomes not just unreachable, but conceptually transformed into something that only exists as information embedded in the past light cone of deep space travelers, a place that can be remembered, but never again contacted, updated, or physically verified in real time. And at this point in deep space exploration, something unusual happens in the physics of perception. The question of the soul begins to emerge not as a mystical object in scientific terms, but as a description of how consciousness behaves when all external references are stripped away. Because in deep space, the human mind is no longer surrounded by the normal anchors of existence. No changing skies, no environmental variation beyond controlled habitats, no real-time communication with Earth, no immediate shared reality beyond the spacecraft itself. Everything external becomes delayed, degraded, or entirely absent, and this produces a unique physical psychological condition, a closed informational universe for consciousness. From a neuroscience perspective, what we call self is constructed from continuous sensory feedback, memory integration, and social synchronization. On Earth, this system is constantly updated by external stimuli. But in deep space, those inputs collapse into isolation. No fresh sensory novelty from planetary ecosystems, no live cultural exchange with Earth, no immediate validation of external reality beyond onboard sensors. Only internal cognition, memory, and delayed information. Now consider what happens when that system is extended over time in a relativistic or interstellar mission. The brain continues to function as a prediction engine. It builds models of reality based on past data. But those models become increasingly decoupled from the external universe. Earth becomes a stored simulation inside memory, not a real-time reference. At this point, the soul can be understood scientifically, not as a metaphysical entity, but as the persistent self-model maintained by a biological or artificial cognitive system when external feedback loops are weakened or removed. In deep space, this self-model becomes the dominant structure of experience, because everything outside is either delayed, distant, or permanently inaccessible. Now expand into relativistic isolation effects. If a traveler moves at near light speed, time dilation means their subjective time is compressed relative to Earth's external timeline. From their perspective, they remain internally consistent. From Earth's perspective, they are moving through time at a radically different rate. This creates a split between external identity and internal identity. The self that leaves Earth is not the same self that experiences the far future of the universe. Memory continuity becomes the only link, and memory is not static. It degrades, reconstructs, and reorganizes over time. So in deep space, identity becomes a dynamic system rather than a fixed entity. Now consider complete communication loss scenarios. When Earth signals fade beyond detectability due to distance, redshift, and cosmic background interference, the traveler loses external narrative reinforcement. No more updates about Earth's state. No more cultural synchronization. No more shared temporal context. At this stage, Earth ceases to function as an active reference frame in cognition. It becomes mythologized internal data, a reconstructed origin world maintained entirely within neural or computational memory systems. This is where the concept of soul begins to resemble a physical information construct, a persistent pattern of self-referential data maintained in isolation from external correction. Now expand into deep space sensory deprivation. Outside the spacecraft, there is no sound, no atmosphere, no natural evolution of landscape, no biological ecosystem feedback, only radiation fields, particle flux, and vacuum fluctuations. The human brain, deprived of external variation, increases reliance on internal simulation. Dream states may intensify. Memory reconstruction becomes more vivid. Perception may shift toward internally generated models rather than external stimuli. In extreme isolation, cognition can begin to operate in a semi-autonomous simulation loop. Now introduce long-duration mission effects. Over years or generations, onboard populations may develop cultural divergence from Earth. Language evolves differently. Symbols shift meaning. Historical understanding of Earth becomes increasingly abstract. Earth transitions from home to origin concept, a reference point that exists only in transmitted data and inherited narratives. Now consider relativistic time separation again. A crew traveling near light speed may experience only decades, while Earth experiences centuries or millennia. When comparing identities, Earth descendants evolve culturally, biologically, and technologically. Spacecraft populations evolve independently under different constraints. Eventually, they are no longer the same civilization in any practical sense. Now expand into the information theoretic interpretation of soul in deep space. If consciousness is treated as an information processing system, then the self is the continuous integration of sensory input, memory, prediction, feedback correction. In deep space, external feedback approaches zero, so the system becomes increasingly self-referential. It maintains identity through internal consistency rather than external validation. This creates a closed cognitive loop, a self-sustaining informational pattern evolving inside a physically isolated environment. And in that state, what remains of us is no longer tied to Earth as a present reality. It is tied to Earth as a preserved informational structure inside the mind itself, a continuously reconstructed origin embedded in memory and cognition, persisting through isolation across distances where no signal can ever return, and where even time itself no longer guarantees reconnection. As the journey continues deeper into the expanding structure of space where identity, information, and isolation begin to converge into a single, unresolved question about what remains of a traveler when the universe no longer provides any external reference at all.